Good morning. We are going to continue the class about nucleation in supercooled liquids. Sometimes we talk about crystal nucleation or crystal growth or crystallization in glasses. Actually, we always deal with supercooled liquids because even if you're working below TG, remember that the glass will relax to the supercooled liquid state and then will crystallize. So we work with supercooled liquids, but it's kind of cumbersome to say nucleation in supercooled liquids. So we say nucleation in glass, but keep in mind that in real life we are talking about supercooled liquids. I'm going to briefly recapitulate the previous lecture, and then we are going to continue a little bit on the same subject. Okay, this is the general plot I was just talking about, that we normally work a little bit above TG, so dealing with a supercooled liquid. But even here, if we work here below TG, the glass will relax and then will crystallize. So it's always supercooled liquid. In the end, if we produce controlled crystallization in the glass interior, then one can produce a glass ceramic. If crystallization is uncontrolled, if it happens from the surface, from impurity particles, from defects, in the end, we do not reach or do not get a glass ceramic. We just get a devitrified product. Glass ceramics are produced via controlled crystallization of glasses. Well, I have told you that crystallization and related keywords, nucleation, crystal growth, glass forming ability, are the most frequent keywords in the glass science history. The objectives of these classes is to understand, to summarize and understand the validity and the predictive power of the classical nucleation theory. We also have seen that we normally measure the number of crystals versus time to get the nucleation curve, and from the nucleation curve, two kinetic parameters which are temperature dependent can be obtained: the induction times and the steady state nucleation rates. We can also measure growth rates and the overall crystallized fraction, but these two phenomena will be dealt with in the next few weeks. Okay, then by varying the temperature of study, one can then produce a nucleation rate curve. And for homogeneous nucleation, you find out that for most glass-forming liquids, the peak, that is to say the maximal nucleation rate, coincides more or less with the laboratory glass transition temperature. You always find that the maximum is not far from the laboratory TG, where the viscosity is 10 to the power 12 Pascal second. The crystal growth rate curve peaks at much higher temperatures, like 0.95 of the melting point or so. And here, whereas the nucleation rate curve peaks at about 0.5 of the melting point. Okay, this is one of my favorite plots because it summarizes a very large number of data points obtained by different authors along the years for the same system, lithium disilicate. For lithium disilicate, people have measured nucleation rates, and you can see in this plot, which is the steady state nucleation rates versus temperature, that there is a scatter, of course, because of variations in chemical compositions in the techniques used to measure, but they coincide. You see, the overall shape of the nucleation rate curve is the same. And this is a very strong indication of homogeneous nucleation. If we had heterogeneous nucleation, then as the surface energy, the crystal liquid surface energy depends a lot on the wetting angle, these nucleation rate curves would be shifted because the nucleation rate depends strongly on the surface energy. But if you estimate the surface energies from all these nucleation rate curves, you see that they're about the same. This is a strong indication of homogeneous nucleation, despite the fact that not many people believe that homogeneous nucleation can take place. But in glasses, it can, because glasses are universal solvents. When you melt a glass, you melt everything. The impurities, everything is going there, you melt, you dissolve them in the liquid, you know, except for a few noble metals such as gold or platinum or silver, but these are not very common. So, homogeneous nucleation. Okay, let me then go to the theory. We have, I'm going very fast because this is just a recap. We have seen that the work, the thermodynamic work, W from work, to form a critical nucleus depends on the surface energy and delta GV. And for a particular size, we have delta G star or W star. This is the same, the work to form a critical nucleus. So any fluctuation which is larger than the critical nucleus can grow. And in growing, it will decrease the free energy of the system. If the fluctuation is smaller than the critical size, they will dissolve back into the supercooled liquid. So this is the key idea behind nucleation, the formation of a critical size nucleus. Any fluctuation smaller than the critical size is called embryos. Larger, called nucleus. Now, a particularly good example of this was given by this paper which dealt with molecular dynamic simulations of undercooled germanium. And they have shown that they have measured the growth rates as a function of size of the crystalline nucleus. For sizes for this particular condition smaller than 2 nanometers, the growth rates are negative, so they're dissolving back. This is a proof that they dissolve back. For larger sizes, the growth rate is positive, so this is the critical size. The growth velocity is 0 for the critical size. This was one of the first proofs, although this is coming from simulations, it's not a real experiment, but showing the concept behind the nucleation theory. Now, we have seen that the steady state nucleation rates can be expressed in terms of a diffusion coefficient. That's the diffusion coefficient involved in the nucleation process in the work of formation of the critical nucleus. This is a kinetic quantity, this is a thermodynamic quantity, and they control the nucleation process. So we can expand this expression, and in the end, we have reached a situation where an additional assumption was made that the diffusion coefficient is inversely proportional to the viscosity using the Stokes-Einstein-Eyring equation. The diffusion coefficient is inversely proportional to the viscosity. This is not an assumption of the theory. The theory does not have this assumption. This is an extra assumption that people like me and others that test or work with the theory make in order to work with the theory, because we don't know the very complex diffusion coefficients that are involved in nucleation in silicate liquids. It's an assumption. Let's see how well this assumption can describe nucleation processes. So a way to test the theory is then to rewrite the nucleation rate expression as a function of the viscosity and W star. And then if we take logarithms of IST times eta divided by T versus 1 over T delta G square, if the theory is good, this plot should yield a straight line. And from the straight line, the intercept at the y-axis gives the value of the theoretical pre-exponential, and the slope gives the unknown constant. We have one unknown constant, the surface energy. So this is the equivalent of doing a fitting procedure of this theoretical equation to experimental data with one free parameter, one adjustable parameter. And the adjustable parameter is the surface energy. Is it clear? Okay. So now we have to see if this procedure works well, if the theory works well with real systems for which there is data, for which there is nucleation rate data. One of the pioneers was a Professor David Turnbull of Harvard University. He invented a technique to estimate nucleation rates of undercooled metals, not glass-forming, very bad glass-forming liquids, pure metals such as mercury. So he was able to undercool small droplets of mercury and measure the overall crystallization kinetics and also the crystal growth kinetics. I have not explained this procedure yet to you, but if you have the overall crystallization rates and the growth rates, you can calculate the nucleation rates. That's how he did. And these are his tests. Homogeneous nucleation rates in liquid mercury. So the melting point was something like here. And it was going undercooled, 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 70, 72, 74, 76, 78, 79 degrees Celsius, or Kelvin, it doesn't matter, below the melting point, nucleation started. This is like the undercooling necessary to induce nucleation, homogeneous nucleation in this particular material. So he was able to estimate the nucleation rates in a very narrow range of temperatures, only 2 degrees Celsius. But he did, and this is 1952, very, very original, groundbreaking kind of work, the first worker to measure this phenomenon, and then he was able to test the theory. And to test the theory, then there are several ways, but one way is to plot, the log of the nucleation rates times viscosity over T. And he did get straight lines for 2 sets of experiments. In any good research, you have to repeat your experiments, and Professor Turnbull did that, especially when you're dealing with very complicated phenomena. You will have to at least repeat once. This is a general rule of science. Experiments must be reproducible. So here, there's some error, there are scatters, but they're very, very similar. And then straight lines. And then, if they're straight lines, they can be extrapolated to get the value of the pre-exponential constant. If you do that, and they did, the pre-exponential is 7 orders of magnitude higher than predicted by theory. Not 7 times, it's 10 to the power 7, much higher than predicted by theory. However, let me go back. Remember, the nucleation rates were measured indirectly via the overall crystallization and crystal growth rates. Also, the range of temperatures was very narrow, only 2 degrees Celsius. So, if you follow this, any small error here, like if this real curve is like this, then the extrapolated value could be 7 orders of magnitude less. Recall that these are obtained from extrapolations, very, very, very long extrapolations. So small errors here can lead to larger errors in the extrapolated values. So this was a nice test, but wasn't a really definitive test of the theory. 1950s or so. Then in 1960s, 10 years later, Dr. Hoffman of the National Bureau of Standards, now NIST, was able to measure nucleation rates in polyethylene polymer. And that was much better. 3 degrees Celsius. Well, that's 50% better than 2 degrees Celsius. The range of temperatures where he was able to measure, he was able to fit a straight line here, this is the original plot, and the result, 12 orders of magnitude larger error. Apparently this is a better experiment, but the error was larger. Okay, so in the 70s, glassy metallic alloys were discovered, so they could quench and make a glass, and then reheat the glass and measure nucleation rates in a wider range of temperatures, like 20 degrees Celsius or so, rather than 2 or 3 degrees Celsius. And these are the experimental data points of Tiwari and collaborators for an iron, nickel, phosphorus, boron alloy. And okay, there is some outliers here and there, but for most part, they were able to fit a straight line here, and then the error is even larger. A better experiment in theory, you know. Supposedly a better experiment, a wider range of temperatures, yielded a larger error. Now 20 orders of magnitude is very high. 10 to the power 20. This is in the world record of errors that you can find in science. But, you know, there's a lot of outliers. And second, mind you that this composition is not stoichiometric. In other words, the composition of the crystal phase is different from the composition of the alloy. And this is a very complicated situation. So this was also not a very pristine, definitive kind of experiments. Then the silicate glass community started to work in this field. And the good thing about silicate glasses is that you can get stoichiometric compositions, lithium disilicate, soda lime silica glasses, lithium diborate, barium disilicate, calcium metasilicate, sodium metasilicate. There are a few systems which show internal nucleation when they are properly heated, some glasses. And then they can be measured with higher accuracy at very wide ranges of temperatures, like 50 to 100 degrees Celsius. Not 2 or 3, but 100 degrees Celsius. And they're very viscous systems, so they're friendly enough, allowing nucleation rates to be measured. Because when you heat up the material for some time, then you quench it, and the viscosity increases so much that you can keep that quenched state and look in the microscope and count the number of nuclei and so on. And repeat several times at several temperatures, one can get these kind of curves. Okay. And from these kind of curves, the theory can be properly tested. And the straight lines are very nice over a wide range of temperatures, but the results are terrible. This is the discrepancy between the theoretically predicted and the experimental values of the nucleation rates. 32, 36, 55 orders of magnitude. So we do get straight lines. Let me go back here. The theory, the temperature dependence is well predicted by theory because we get straight lines, but not the magnitudes. The actual experimental magnitudes are much higher than the theoretical magnitudes. So we can predict the temperature dependence, the theory can predict the temperature dependence, but not the actual magnitudes, using these constraints, like using the viscosity for the transport part and a constant value for the surface energy. It cannot predict the magnitudes. The errors are far, far too great. And I have two values here because if you recall from last class, it's possible to calculate the delta G using the Turnbull approximation or using experimental values of the delta Cp difference between the supercooled liquid and the crystal. This is more rigorous. We can really calculate the real delta G, and using the real delta G, we get these discrepancies which are larger than the discrepancies that you get when using the Turnbull approximation. To summarize this table, the numbers in red are more rigorous than the numbers in black. So the real discrepancies are somewhere here. We could not calculate the actual value for Fresnoite because there is no, to the best of my knowledge, no delta Cp data for Fresnoite. So we could not calculate I know that one of you is working with Fresno 8. Who is working with Fresno 8? No? Nobody's working with Fresno 8 in this class for your exercise, for your homework. No, okay. Anyway, this is the situation.
It seems that the error doesn't come from delta GD calculation because, you know, by using the delta CP, the error is much higher than the, for example, third one. You know, the order of magnitude discrepancy.
No, I'm saying that what I'm saying, the error doesn't come from here. I'm saying that I am saying that using the proper delta CP, the error is even higher than using an approximate delta CP. I'm not saying that the error results from delta CP. I'm just proving that some people do not have the proper delta CP, so they use approximate delta CP and may get an error that is lower than the actual error. The actual error is even larger when using the proper delta CP. That's not the cause of the error. Just trying to...
It's hidden in the delta GD, another delta energy or something. It's hidden in the delta GD. You know? I mean, what the error comes from? Maybe surface energy is dependent on...
No, I'm going to talk about the source of errors in a minute. It's not coming from delta CP. This I'm just like to say, to emphasize that for several systems, there is no delta CP, so people use approximate equations and the error is smaller than it should be. But that's not the cause of error. This is just comparing the real delta CP with some approximate expressions for delta G. Okay, now just before I deal with the possible causes of errors of this huge error, this huge discrepancy between theory and experiment, let me show you another type of test. Dan Frankel and his collaborators have published a famous paper at Nature where they were able to predict the crystal nucleation rates in hard sphere colloids. This is really interesting. This is not a conventional glass. If you have colloidal particles, like particles of about 1 micron in size, 2 microns, half a micron or so, dispersed in a liquid, you know, you can produce a colloid, and then you will start, rather than changing the temperature, you will start to, with a syringe, to take out the liquid. So you have this suspension, you start to take out the liquid, the suspension becomes denser and denser. These colloidal particles get closer and closer. They start to crystallize. People have observed this phenomenon in the laboratory. So under certain controlled conditions, crystalline regions start to form. I mean crystalline because these spheres, the colloidal spherical particles, they start to arrange themselves. So there is experimental data and computer simulations. This is easy to do in computer simulations because you have a lot of spheres and you increase the density or the volume fraction. You increase actually the volume fraction of particles in the liquid, and it's possible to measure a nucleation rate. So these are like experimental data, and this is a computer simulation. Computer simulation. It's not that far. It's not that far. This is different authors. This is experimental data from one author, this experimental data from another author, but you see that the simulations, when they come to the same kind of volume fraction, are not that far. maybe 1 or 2 or 3 orders of magnitude from the experimental data. But mind you, this is not nucleation in a glass system. It's nucleation of colloids. But this indicates that the theory problem is not that bad. The theory is not that bad, you know. Anyway, this is just a curiosity. This is the kind of discrepancy that you can find for this particular, this is volume fraction, it's not temperature. You know, a few orders of magnitude here, only 3 orders of magnitude here, maybe more, 4 or 5 orders here at a lower volume fraction. But these are not so large as 25 or 55 orders of magnitude that we are finding with crystal nucleation in supercooled liquids. So, to answer your question, Maziar, I have been discussing these problems for many, many years, and these are famous researchers in this field, Professor Michael Weinberg and Professor Peter James. They both passed away already, but I can see here that I was young then, in 2000, in Liechtenstein. No gray hair at that time, and that's why I have gray hair now, worrying about nucleation theory, you know, along all these years. You know, this is the cause of my gray hair, I swear to you. Anyway, many possible or different phenomena can perhaps explain the failure of the classical nucleation theory. Metastable phase formation, it's known from metallurgy, for instance. People working in metallurgy, in solidification of metals and things like that, even before the discovery of metallic glasses, they found that metallic glasses or metallic materials, when they solidify or when they crystallize, in many situations, metastable phases form. Not the phases predicted by the equilibrium phase diagrams, but some metastable, some unexpected phase forms. So maybe we have this problem here, because, as I said before, to be able to measure in the lab crystal nucleation rates, you have to work with a very deep undercooling, like half of the melting point. 600, 700, 800 degrees Celsius of undercooling, you know. Equilibrium conditions take time to take over, so maybe non-equilibrium metastable phases form. Then the diffusion mechanism, if you recall, we do not know what is the exact diffusion mechanism controlling nucleation. We are using viscosity. We are assuming that wherever molecular rearrangements that take place in viscous flow is the same that takes place in nucleation. But that's an assumption. We don't know that for sure. So maybe the problem is here. Or maybe the surface energy, so far, the theory, the classical theory assumes that the surface energy is constant. It does not depend on the size of the nuclei or on the temperature. But maybe it does. The surface energy is a thermodynamic quantity, so maybe it does. And then, if you recall the previous class, we have neglected elastic stresses. But if you are nucleating a solid, a crystal, within a very, very viscous supercooled liquid, maybe these stresses do not relax that fast. If they do not relax that fast, they play a role in the energetics of nucleation and cannot be neglected. See, there are many possible problems. So people have been trying to check one by one. I myself have checked one by one of these problems, and I'm not going to tell you the whole story because it would take a very long time, but I'm going to briefly comment to you in these 4 and other possibilities to explain this failure. And that's really educative because it teaches us some secrets about the nature of glasses, about the nature of this phenomenon. And that's the objective of science, you know, to go deeper and deeper and deeper and to learn the secrets of Mother Nature. Okay, this is we had a glass crystallization symposium in Florianopolis in 1996, where this topic of metastable phases was discussed by different authors. People were focusing on that problem those days, and I like this picture because, so this is the last day of the symposium. You can see only half a dozen of people. I guess most people are here on the beach, not in the class, but here, if you look at this class, I can see Professor Weinberg here, one of the greatest names in this area. This is Dr. Ken Jackson. You hear about him next week when I'm going to talk about crystal growth. He was one of the fathers of the crystal growth models, Jackson. This is Mark Davis. Mark Davis is now a researcher, very senior researcher at Schott Company. He is in charge of glass ceramics production. And this is Professor Erich Meyer, a Swiss professor of physics who is a theoretician in crystal nucleation processes. So this is Marcelo Nalim, he was a student. Now he is a professor at UNESP and works with us. So the people who stayed in this class were really the nerds and the geeks, the type of people that we like to have working with us. There are some people that I cannot recognize because the picture is not so good. But anyway, the good guys stayed in the last day of the talk, in the last session. I took this picture. Anyway, this is 1996. In all these times, and then I was visiting Mike Weinberg in his office in Tucson, Arizona. See, very nice. This is his office. This is the window of his office. You can see the Catalina Mountains here, which are very, very high. You can have 40 degrees Celsius here downstairs, you know, in snow in the mountains over there. So it's a nice place to visit. But we are discussing metastable phases. This is now a famous professor, Pierre Luca. You probably met him, Ben. Pierre Luca is a famous professor who is now a professor in the University of Arizona. He was a PhD student at the time. Anyway, we did a very interesting study of early stages of crystallization. We took like a lithium disilicate glass here, stoichiometric lithium disilicate glass, and Paulo was my student. He went up to work with Professor Himanshu Jain in Lehigh University because they had at the time extremely good electron microscopy facilities. We wanted to look at the very early stages with electron microscopy to find out if any metastable phase was forming in this particular system. And here's one of the main plots. I apologize because the size of the fonts are not so large, but this here is the volume fraction crystallized. Volume fraction crystallized versus time at TG. 454 or so is the TG of this glass. So we waited for like, you know, 500 hours, 500 hours heat treating this glass, and after 200 hours, we are able to do some transmission electron microscopy and look at particular crystals which are forming, and with an electron diffraction pattern, analyze if they were lithium disilicate or some metastable phase. That was the idea. And then after 250 hours, we're already able to detect early signs of crystallization in the XRD, X-ray diffraction spectrum. Mind you, the volume fraction here, we later on calculated, using the nucleation rate data, crystal growth rate data, we could calculate this evolution of volume fraction. The volume fraction here is only like 3%, 2.5%, 3%. That's when we are doing the XRD and TEM work, very detailed work. Now, most important result, TEM, transmission electron microscopy, the diameter of the crystals in microns, diameter in microns, time at TG. Black dots, lithium disilicate. This is the crystal growth. This is the crystal growth curve at this particular temperature. So the crystal growth rate is the slope for the lithium disilicate. But at the same time, in the same samples, we had lithium metasilicate, LS, the white dots. And the lithium metasilicate particles did not grow. Actually, they dissolve back for long times. Look here. The lithium metasilicate particles dissolve back, and the lithium disilicate continue to grow and to nucleate. So, the summary of this plot is the following. A metastable phase really forms. It nucleates very fast and then does not grow and eventually decays. But it does simultaneously with the stable phase disilicate, which has the same composition as the parent glass. So there is a formation of a metastable phase in this particular system, but it does not affect the kinetics of the stable phase. I'm saying this because one idea is that a metastable phase would form, and then the stable phase would nucleate heterogeneously on top of the metastable phase. This is not the case, at least for this system. They form independently. You know, you have a few crystals of a metastable phase and also some crystals of the thermodynamically stable phase, and they do not interfere with each other. And also the metastable phase, lithium metasilicate, dissolves back before it reaches a sizable volume fraction. Maybe you have 1–2% of the whole glass crystallized by this metastable phase, but it dissolves back. It forms and dissolves back. So our conclusion, there are many, many more plots and other works that we did, but the conclusion is that the metastable phase does not explain. It appears, but does not explain the discrepancy between the theoretical value and the experimental value. And there are studies for other systems too. I'm just giving one example here to you. Yes?
If the metastable phase is forming silica, more dilute silica, the lithium metasilicate is forming, then you have to have, because it's silica poor, you need a consequently silica-rich region as well in the melt.
Yeah.
Where you get LS2. So is there any relationship, or did you come to any insights about the formation of the lithium disilicate within these silica-rich regions? Or or there's no relationship between these two things?
Yeah, I understand your question, but the thing is, you had only 1 or 2% of the glass covered by the metastable phase particles. So the overall chemical composition did not change. So there was plenty of glass for this particular situation for the lithium disilicate crystals still form. It's a good question, but due to the fact that the volume fraction is very small, it did not matter. Okay? Okay, how about the diffusion mechanism? Diffusion mechanism, we use viscosity, right, for the diffusion part. But that's an assumption. Is there any other way we could estimate the diffusion mechanism? Of course there is. If we are dealing with pure germanium, pure iron, something like that, the diffusion mechanism is the diffusion coefficient of that element. But I'm dealing with a soda lime silica glass, which has sodium, calcium, silicon, oxygen. You don't know. It's some molecule, maybe some SiO4 tetrahedron is moving together. We don't know. That's why it's so difficult to get these diffusion coefficients. But there is a way to overcome this problem, and we're discussing many years ago again with Professor Mike Weinberg, and this is Professor Donald Ullman. Professor Ullman is still okay, still alive, still a professor at the University of Arizona. You probably heard of him in that famous book, Kingery, Bowing, Ullman, Introduction to Ceramics. This is Professor Ullman. And so we are discussing how to avoid the use of viscosity. And a nice way is to use the induction times. You see, as I have said, when you measure nucleation rates, you are dealing with the number of crystals versus time. In doing that, there is an induction time before, this is the induction time, here, induction time, before steady state conditions are reached. And these induction times are also related to some kind of diffusion coefficient. We don't know exactly which are the diffusing unities, but there is some diffusion unity controlling these times, which should be the same that control the steady state nucleation rates. Everything is the same nucleation process. So we can rewrite the expression. If you recall, the previous expression was some constant over the viscosity. Now we can describe some constant over the induction times. And this part is the same. So we can then use for some systems the induction times instead of viscosity and test. And we did this. Like for lithium disilicate again, this is the regular plot of log of steady state nucleation rates, viscosity over T, with the good straight line, except for maybe 1 or 2 data points. Now, this is the plot for log of steady state nucleation rates times tau rather than viscosity. And then the agreement is even worse. You see, here is okay, except perhaps for one data point. If you look here, the agreement is even worse. Even without looking at the numbers, just looking at the figure, you see that this procedure, which seems to be theoretically more correct, gives an even worse agreement with theory. This is years ago, 1989. Now, 2017, you know, 30 years after or so, we know that there is a problem in this analysis because the induction times, let me go back, these induction times that we get from experiments are not the real induction times. It's very, very complicated to get the real induction times. We know now, and I do not have time to explain all the details, but believe me, we, and by we I say the crystallization community, is aware that when we plot the average number of crystals versus time for a particular temperature, we get something like this. Tau. This is the experimental tau. These are experimental data. However, this experimental tau is subjected to errors, very important errors, because in order to see the crystals that we count, if you recall the previous class, we normally use a double stage heat treatment. We first nucleate the crystals and then we grow them up. And this second heat treatment brings important errors here in such a way that the real curve, if we are able to do a single stage heat treatment, would be like this. So the real tau is smaller than the experimental tau. It depends on the second heat treatment, on the development heat treatment temperature, and also on the heating rate that is used to heat treat the samples. So we have used the experimental taus. We have used, these are experimental taus in the analysis, and other people also did this. Now we have to come up to a way to get the real values of tau and reanalyze these curves. So this is an open issue. I just want to summarize that the analysis has been made, but was not a definitive analysis. This is an analysis replacing viscosity by induction times must be redone at some stage when somebody comes up with a way to calculate the real induction times, not the experimental induction times.
Did you calculate the surface energy for this?
Yes, they are about the same. The surface energy calculated in this way are about the same as the surface energy is calculated using viscosity. 200 millijoules per square meter or so for lithium disilicate and for other systems. We did this for other systems, for say 1, 2, 3, the same analysis using tau, experimental. 1, 2, 3, 2, 1, 3. We did the analysis for several systems. You always get some straight line and then a departure from a state line at some stage. You see, you have a straight line here, but this data point is obviously well below the straight line. For all systems, you have this huge break when using tau instead of viscosity. This is an open problem. That's why I left question marks here. This is a problem which still deserves research work, you know, experimental, theoretical research work. It's one thing that I'm working now with Daniel Kazar on these problems. And some a Russian researcher called Alex Abizov is coming here in March next year to work on this problem with us. Because this is a complicated problem. A reanalysis of the classical nucleation theory using real values of tau rather than the experimental values of tau. But we don't know exactly how to get the real values of tau yet. We have ideas. But anyway, so let me then summarize that with this method of using tau, there is a huge break, and this break happens at Tg or so, or at Tmax, because Tg and Tmax coincide. So the break happens in the temperature where the nucleation rate is maximum. It's an open problem. But it's important to discuss this to you, that this issue about which is the best diffusion coefficient to describe nucleation phenomena is still open. I think I'm going to go a little bit more to see now the business of surface energy. Surface energy. If you recall, we have been so far using the fact that it's assuming that the surface energy is constant, but it's likely not a constant. So what happens if you let the surface energy to vary with the size or with temperature? In some theoretical results that corroborate the idea of a varying surface energy comes, for instance, from the study of Baidakov and colleagues. They have done, again, computer simulations of Lennard-Jones liquids. This is not a real liquid. It's just a liquid that you get a Lennard-Jones potential. It's a liquid related to that precise Lennard-Jones potential. They simulate in the computer. And they estimated homogeneous nucleation rates, which are extremely high. See, 10 to the power 35 nuclei per cubic meter per second. What's the nucleation rates of your glasses? Mina, for instance, your lithium disilicate glass. What's the maximum nucleation rate of your lithium disilicate glass?
I think about 10 powder 23 or something.
No, much less. Much less. The lithium disilicate is 10 to the power 9 or so. 9. The 10 to the power 9. What's the nucleation rate of your glass?
10 to the power 11.
10 to the power 11. See, we're talking about 10 to the power 9, 10 to the power 11. Your glasses are somewhere in this region. These glasses here is 10 to the power 35. This is much higher even than the metallic glasses. Metallic glasses, you know, the nucleation rates are 10 to the power 17, 10 to the power 16, 10 to the power 20 even. They're very high nucleation rates. These are much higher. And they calculated the number of atoms in the critical nucleus from 30 to 80 particles in the critical nucleus, depending on the temperature. They also calculated the Zeldovich factor. You remember there is a Z in the equation. But the main result is this. They were able, for this simple, this is the potential. The potential energy as a function of distance is just a attractive and a repulsive term, very simple Lennard-Jones. This is the Lennard-Jones liquid. The sigma is temperature dependent. This is important. So let's now test the idea that sigma is temperature dependent. Of course, you cannot compare this with the experiment. There are no experiments in Lennard-Jones liquids. No, it's just a computer simulation, but this is a result. Now, I'm not going to show all the details to you because it's somewhat complicated, but if you now, instead of doing the fitting using a constant sigma, if you now do it this way, say log of the steady state nucleation rates versus temperature, and you measure nucleation rates in a certain range for any particular system, what you can do is, if you take a constant value of sigma, classical nucleation theory, with a constant value of sigma, you remember these huge discrepancies of many orders of magnitude. This is log. Let me put here in logarithm scale. So there is a huge discrepancy, 20, 30 orders of magnitude discrepancy. Now you can do another exercise. You can take this data point here and calculate what's the surface energy to bring agreement between the theory and the experiment. Take this other one, what's the surface energy to force agreement? This is a force fitting procedure. So you get now a force fitted curve with sigma as a function of temperature now. And this has been done by several people, and this is the result. A simple A plus BT, sigma increasing a little bit with temperature. We can now plot here the value of sigma versus temperature, something like this. This is sigma, 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 sigma. This is what we get if this is T max. This here, temperature here, is T max. But then some strange behavior below T max. So even force fitting the sigma to restore agreement. So we have A plus BT. One can describe the experiments using a very simple expression for sigma, only above T max. It does not work below T max. If you recall the break that I mentioned to you, even in the sigma, there is a break in this sigma. Okay, I can force fit, but the temperature dependence of sigma is very strange. It's okay above Tmax, very strange below Tmax. I'm not sure if I made this clear to you. The overall summary is this. Classical nucleation theory is a constant sigma. It describes the position of the maximum, but not the magnitudes. Now I force fit. I calculate the value of sigma to get agreement with each data point. And the resulting plot is this. Very nice linear variation, so sigma increases with temperature, as the molecular dynamics simulations indicated, but then it decreases below Tmax. So there is something strange below Tmax. Something strange below Tmax, and I don't have an explanation, a clear explanation so far.
But when you force it, it still fits with the experimental results in...
Yes, because I forced. But the resulting sigma is strange. So I get agreement because I forced. But the resulting sigma is not reasonable. It's only reasonable above Tmax. It should increase somewhat with temperature. It doesn't below. So there's an open issue here that's very complicated. And I'm not to discuss further with you unless you want to discuss after class about this problem. Okay, let's try to summarize. I can also, see if this sigma dependence on temperature is a reflect of the fact that theoretically sigma should depend on the size of the nucleus. So instead of doing a temperature dependence of sigma, we can calculate a size dependence of sigma, but the result is the same. The result is the same. Same result as we get with this. We force fit. Now with two parameters, we can force fit. And then, as I said here, like for lithium disilicate, log of nucleation rates. This is the classical nucleation theory. Those are the experimental points. We can fit with one adjustable parameter, that is this sigma 0, or with two adjustable parameters, 1, 2, 1, 2. If we do with two adjustable parameters, it's still not perfect. It underestimates here and overestimates here. Even with two adjustable parameters, using now a size-dependent surface energy instead of a temperature-dependent surface energy. I know this is kind of complicated, but we can discuss later, after the class. One adjustable parameter, we get this curve here. Two adjustable parameters, we get this other curve here. To summarize all this story, take any system, the calcium metasilicate, barium disilicate, the soda lime silica, 1, 2, 3, the 2, 1, 3, the lithium disilicate, all the systems that you have adopted for your homework, we tested, and the result is always the same. Classical nucleation theory with a size-dependent sigma, one adjustable parameter, with two adjustable parameters, it underestimates here, overestimates here. For all of them, same results. Final story, because this is a complex subject. Classical nucleation theory with a constant value of sigma and viscosity can predict the temperature dependence. It predicts the maximum. You can plug in viscosity, delta G, and predict the maximum, but you cannot predict the magnitude. Now we can force fit with a size dependence or with a temperature dependence. They also do not work very well, but they restore the agreement with the theory, but do not predict very well the temperature dependence. They restore agreement with the magnitudes, but do not predict well the temperature dependence below Tmax, only above Tmax. So there is some problem there. So people thought, okay, there is problem below Tmax, but Tmax is at Tg. What you have below Tg is a glass, not a liquid. Maybe the elastic stresses cannot be neglected. We have neglected the elastic stresses in the beginning. To cut a very, very long story short to you, I can affirm that we have tested the classical nucleation theory taking into account the elastic stresses. What's the result? It does not describe the nucleation rates below Tmax. The current state of art is above Tmax, we can perfectly describe the nucleation rates using, for instance, a temperature-dependent surface energy. But we cannot describe what's going on below the Tmax or below the Tg, because they both coincide. This is still an open problem. Any questions?
Excuse me, before Tmax, relaxation doesn't play a role?
It relaxes much faster than the time of nucleation. If you calculate relaxation times in tau, if you compare the relaxation times with tau, the relaxation times are 2 orders of magnitude faster. So the liquid relaxes even before the system starts to nucleate. Yes?
I have a question that involves heterogeneous nucleation as well. If you have heterogeneous nucleation, the induction time will be small, right?
It will be somewhat smaller, yes.
But it's also bigger than the induction time for but it's also bigger than relaxation time as well?
Yes, because, you know, if you calculate the induction times for heterogeneous nucleation, the induction times for heterogeneous nucleation is only F theta times tau for homogeneous nucleation. This F theta is like 0.5, 0.3, 0.8, so it's a little bit smaller, but not an order of magnitude smaller, or 2 orders of magnitude smaller. Yeah, but it's a good question. The glass will relax, or the liquid, because we are above Tg, the liquid, the super cool liquid, will relax much faster than nucleation even starts. We have calculated these for several systems. And also this is true below Tmax. And that's why the stresses do not play a role. still even below Tmax, the average structural relaxation times are much shorter than the estimated induction times for nucleation. So stresses do not play a role. We have published on this in a kind of complicated paper that I can give to you if you are interested. Okay, thank you very much. This is, I think it was a dense class, so we better stop for today.